Today's paper is DeepBox, Learning Objectness with Convolutional Networks. The method introduces a data-driven semantic approach for ranking object proposals. To do this, it uses 4-layer CNNs to re-rank proposals generated in a bottom-up manner. The object proposals are category agnostic, meaning object class is not considered. It generalizes well even to the unseen object categories. In summary, the use of DeepBox with FastR CNN model achieves better performance compared to the FastR CNN and EdgeBoxes pair. Now, the figure shows the framework of DeepBox. Given an image as an input, initial object proposals are generated. Here, any of the existing proposal algorithm can be used. This could be typical methods like selective search or edge boxes. As shown in the middle image in the figure, the initially proposed boxes are randomly generated, so meaning the numbers represent the order of the box proposals, and we can see that the number has nothing to do with the quality of the boxes. So what DeepBox does is this DeepBox module takes these box regions as input and re-ranks them. The result after the re-ranking process is shown in the rightmost image. The boxes bounding the cars are now assigned lower indices, which means that it has higher scores, and large boxes covering the background-like regions have higher indices, which means that it has low scoring. Now, on the left is the architecture of the 4-layer DeepBox model. It's composed of 2 convolutional layers and 2 fully connected layers. The numbers in the convolutional layer denote kernel size, output channel, and the stride value. The pooling layer has a kernel size of 3 and stride value of 2. The output dimension of the first fully connected layer is 1024, and the final output dimension of the last layer is set to 2, which is used to represent the objectness score. So because running CNN on highly overlapping boxes wastes computation, so borrowing the idea from SPPNet, the convolutional part of the network is shared among the proposals. Meaning, instead of running the network multiple times in each box region, convolution is first applied on an image and the regions are extracted in the feature after the convolutional layer. To know more about this idea, I suggest reading the paper called SPPNet. Now, the training process is composed of 2 stages. In first stage, it uses sliding window to get positive and negative object samples, region samples. The aim is to distinguish between object boxes and randomly sampled boxes. Randomly sampled boxes, think of it as a background regions. So it scans through the region, and if the intersection of a union between the candidate and the ground truth is less than 50%, it's 0.5 here, then it's considered as a negative sample. And if the intersection of a union between the candidate and the ground truth box region is if it's greater than 0.5, then it is considered as a positive sample. And in stage 2, similar process is it's a similar process, but the aim is to train on harder negative samples. And its purpose is to do better at the errors made by the proposal methods. The authors concentrate on this method called edge boxes. I suggest reading this paper as well. So the purpose, as I've said, is to let the algorithm work well on hard negatives. The difference between stage 1 is that it's using a different algorithm. Instead of using sliding window, it's using edge boxes. But here, To filter out positive and negative candidates, a different threshold is used, as it's written here. If intersection over union between the candidate box and ground truth box is less than 30%, which is 0.3, then it's taken as a negative sample. And if the intersection over union is greater than 70%, 0.7, then it's taken as a positive sample. So what happens to the boxes between 0.3 and 0.7? So reading the paper, it says there they are not taken as a training data set. So it only considers boxes having intersection over union less than 0.3 or boxes having intersection over union greater than 0.7. Now, this table shows the comparison of the DeepBox method with other object proposal algorithms. As it's shown in the table, area under the curve score of the DeepBox is higher than other proposal methods. Also, the recall rate is higher. Compared to selective search, recall rate is the same, which is 87. But if we look at the time, it is much faster. So DeepBox is better than selective search and all other proposal algorithms. And on the right is the result of DeepBox when it's paired with object detection model, which is FastRCNN. From the top, FastRCNN with selective search, which makes about 2,000 proposals. Mean average precision score is 35.5, where when using FastRCNN with edge boxes, we get a mean average precision score of 35.9. And lastly, we see that a FastRCNN with DeepBox pair, it makes about 500 proposals. So it's taking only the best 500 proposals. And when using this, they get a mean average precision score of 37.8, which is higher, about like 2% higher than edge boxes and selective search. Now, lastly, this shows the qualitative results of DeepBox and edge boxes algorithm. So it's an image pair. So on the left is the result from DeepBox ranking, and on the right is the ranking from edge boxes. As it's shown, DeepBox has a higher recall of the object box candidates, especially in the highly cluttered scenes, like in the cars. We see that, well, green boxes are the ground truth boxes, and the red boxes are ground truth boxes that are missed. So if we look at the image of the cars at the bottom, DeepBox it makes better proposals compared to the edge boxes. So if we see edge boxes on the right here, it has lots of red boxes, which represent ground truth boxes that are missed. A link to the paper and some useful resources will be provided in the description. That's all for today, and I'll see you next time with a new paper.